In this video, we'll be talking about the role of capacitors in circuits, particularly around supplying power to digital circuits, digital electronics. Now, first let's recap what a capacitor actually does. What we're trying to do is store an electrical charge or electrical energy in an electric field. Inductors, on the other hand, store it in the magnetic field. Now, basically the common type of capacitors we use have two conductive plates, and they're separated by some non-conductive material. We call that non-conductive material or substance a dielectric. Basically, they operate a bit like a rechargeable battery that can charge up really, really quickly. So taking all the chemistry and everything out of it, they're doing a similar sort of role. And they have many, many cycles that we can charge and discharge, rather than the battery has a fairly low, in comparison, finite number. Now, there's three main things that we actually use capacitors for around the digital electronic circuits. The first one's decoupling or bypass capacitors. Next one, we call them dump or smoothing capacitors. And finally, we have powering things or supercapacitors that we'd use for this. So let's go through each of these and see how they actually look and how we actually use them. Now, decoupling capacitors we should always use when we're talking about digital electronics. And basically what we do, we connect between power and ground for each supply pin of our digital logic device as close as possible to that pin, a capacitor. And typically when we're dealing with frequencies of less than gigahertz, we use 100 nanofarads capacitor. That's the magic number of a capacitor. And these are little ceramic capacitors, so 0805 or that sort of size. We put them next to each of these pins. So if our microcontroller has 3 VCC pins, we put 3 of these in nice and close and then directly to ground. Basically what these capacitors are doing is they're opposing the quick changes in voltage we get and filtering out those small voltage spikes that can occur. And any switching that's occurring within our microcontroller, and remember there's lots of transistors in these things, they're always switching, it'll stop that switching noise going out onto our power supply lines and going to the rest of the circuit. So we're kind of decoupling our microcontroller from the rest of the circuit and stopping that noise going in both directions. Well, our next type of capacitors are our dump capacitors or our smoothing capacitors. And sometimes we need a large amount of current, sort of a chunk of instantaneous power for a short period of time. Good examples of this are motors, where we start a motor, and basically when a motor starts up, it uses a huge amount of current, and then it gets lower as the back EMF kicks in, and we have a lower current that's going through there once the motor is actually spinning. Things like flashes on cameras, things like communications modules, where we're sending out data in quick bursts. The instantaneous current that are required by these can go quite high for a short amount of time, and then it will drop back down again. Now, what can happen with our batteries and regulators is they might be too slow to react to this, and our voltage supply will dip as a result of it, and leads to brownouts. Now, microcontrollers don't like brownouts. Typically on brownouts, what happens is they have a built-in reset mechanism where detects a brownout, voltage goes too low, restarts from scratch, and we wonder what's going on. Every time I try and take a photo or drive a motor, the thing resets. That's why. Well, the way we deal with it is we use a larger value capacitor. So not a little 100 nanofarad capacitor like what we had before, but we're using something like 100 or 200 or 300 microfarad capacitor. This capacitor provides that instantaneous power that's required for a short period of time and stops the voltage line dipping too low. Now, things we need to consider with these, we of course don't want to exceed the maximum voltage for the capacitor because they can blow up. We don't want to put them in back to front because they can blow up. And back when I worked at NEC, one of the standard tests that were done, whenever you turn on the board for the first time that was a prototype, you'd wear safety glasses just in case they did blow up and pop out of the board. Now, I remember way back in first year, the group behind us working in the lab, we heard a massive bang, and that's exactly what happened. The capacitor flew out of the board and hit the roof, left a little bit of a mark on the roof, and we remembered from then on, make sure you put the capacitors in the right way around, not the wrong way around. Well, that leads us to our third type of capacitor, the capacitors for power, for powering things. And these are much bigger again. These are what we call supercapacitors. Now, these have typically capacitances above a farad. Before we were talking about a large capacitor being 100 or 200 or 500 microfarads. Here we're talking about a farad, so something much, much, much larger. But they're typically lower voltage, so most of these are below 5 volts. Now, there's many applications you can use these to replace batteries, particularly when we're dealing with low power operations or when we're using some power scavenging where we're trying to get energy from the environment to charge up these capacitors. They've got lots of pros behind them, like many, many, many recharge cycles, really fast charging times and a long working life, and higher discharges, but they've got lower capacities overall. So if you need something with a high capacity, not a high instantaneous capacity, but a higher capacity, well, you go with batteries, not these. And they're also higher cost per unit of capacity compared to a battery. This nice little table here puts some figures and quantifies supercapacitors versus lithium-ion batteries. Now you'll see, for example, in the charge time, those supercapacitors charge really, really quickly. We're talking in under 10 seconds, where our lithium-ion batteries, even with fast charges, we're talking in the order of minutes or maybe even an hour. And also with the life. So 1 million charges or discharges with a supercapacitor compared to only maybe 300 to 500, or maybe a bit more with the lithium-ion batteries. And that's why if your laptop's a few years old, you've probably done those 500 discharges and your battery will be on the blink and won't be charging up and giving you the full charge that you had before. Same with your mobile phone. You've got your different voltages there, and we see the power that's allowed by our supercapacitors very, very high. Our cost per kilowatt hour is significantly more expensive with our supercapacitor, and our service life is significantly longer with the supercapacitor. But the actual capacity of these supercapacitors, at least per unit dollar, is much, much lower. They get quite expensive.